Okay, this is chapter 20, example 1. We have one example for this chapter, at least so far. Once again, it's very low level. It's hard to come up with meaningful examples, so happens to be one of them. So this is circuit very much like the last example we did, where the heart of the circuit is a NAND latch, and what we want to do is to be able to control the operation of this NAND latch with an external button. And so that means if I press the button, I want to have the circuit act like a latch. Otherwise, if I don't press the button, I want this circuit to not change its output. Another way to put that is, if I'm pressing the button, this circuit's going to act like a latch. If I'm not pressing the button, the circuit holds its state. First black box diagram. It has two output. It is a latch, so this is going to be Q bar and Q. And we got S, R, and a button. And that is our top level black box diagram. So lower level in this is, we know it has a latch. Input side, we have S and R, and what we're going to need to do is drop some logic in here to make this circuit work. So once again, what I need is a gate such that the button is pressed. Okay, and this is actually wrong. Okay, we got it right here. Essentially, if I press the button, I want the output of the circuit to enable these inputs here. Otherwise, if I'm not pressing the button, I want to disable these inputs. Couple ways to do this circuit. I'm going to take a stab at it, and I'll probably be wrong. No big deal. If I'm wrong, I'm going to check over the answer, and at that point, if it's wrong, I'll fix it. And so what I'm thinking here is that these need OR gates on them, and at this point, I'm going to say, well, maybe it's done. Okay, so if the button is pressed, the output of the circuit is a 1 and a 1, and that is the hold state for this circuit, which is not what I want. So when the button's pressed, I want this to be the circuit to act normally. So I want the opposite to happen. So we have a couple different options here, I believe. Well, I think it's just one option. I think these need to be NOR gates. We'll check that out here. And we'll start off by drawing a truth table for NOR gate. That means if anytime input's a 1, the output's a 0. So input's a 1 to these gates, the output's a 0. Heck, that's not what I want either. But I'm still suspecting that these can be gates here. And what I'm thinking now is these need to be NAND gates. So we'll redo that. That way to analyze this, we'll change these to NAND gates. Okay, so the way to look at this is that these are AND type gates, or actually NAND gates, but anytime there's a 0 on the input, the output's a 1. You can see that with these 3 rows. There's a 0 in there. That means output is always a 1 if there's a 0 on the input, which relates to an AND gate. So that means if the button is not pressed, the output, that means it's feeding these NAND gates zeros, which means the outputs of both these gates are 1, and in that case a 1 and 1 is the hold condition for the NAND latch, and that's what I'm looking for. So when I press this button, these gates are kind of like feed through. They actually act as inverters. But check this out. What's really nice about this problem, we've got these matching logic levels, we'll say, essentially bubble matching, and it becomes an issue like, essentially it's like the NOR latch problem we did before. So this is going to be the optimal solution right here. We don't need NOR gates here. We actually need NAND gates.